Okay, I'm now going to work through problem 2 on your additional problems that you can find on Sakai, entitled Additional Problems and then Fera. So problem number 2 looks something like this. We've got a plane and an incline, and then we've got a cart which looks something like, well, I guess a little tank like this, and the cart starts rolling down here, and then once it gets to the bottom here, it fires a projectile in this direction, so it fires the projectile in this direction and then gains additional velocity. So the first thing that we need to find is the cart rolling down the incline to this point here will just gain velocity due to the fact that it is at an elevated position. So its potential energy will be converted to kinetic energy at the bottom here. So if that height, as the problem says, is 1.25 meters above ground, the first thing that we can calculate is what is the velocity of the cart at the bottom here before it actually fires the projectile. So let me call that velocity 2. We can calculate that by making use of conservation of energy, namely by saying that the kinetic and potential energy over here must be equal to the kinetic and potential energy over here of the cart before it fires. Okay, so we've got, let me call this position 1 and that here position 2, so that we've got T1 plus V1 is equal to T2 plus V2. And the initial kinetic energy is 0 at the top, and the final potential energy is also 0. So what we have is that the initial potential energy goes over into the final kinetic energy. So what we have is then mgh, and if I choose this here as being at 1.25 meters, then I've got my h, and this is at 0 meters, must then be equal to 1/2 mv squared. Immediately the m's drop out, and we've got 2gh is just equal to v squared. 2 times h, that's 2.5 times 10 is 25, is equal to v squared. That means v is equal to 5. I'm going to call this v2, so v2 is equal to 5 meters per second. So that is the velocity of the cart here before it has fired the projectile. Now, the next thing that we need to do is we need to then take the projectile firing into account. The projectile gets fired in this direction at a relative velocity of 0.6 meters per second relative to the cart. Now, the cart and the projectile at the bottom here, their combined mass is 3 kilograms, and then the cart shoots the projectile in that direction. So in other words, backwards, with a relative velocity of 0.6, making the cart actually go faster in the direction that it had been traveling in, and the projectile will obviously go slower into this direction. Does it go slower than 5 meters per second? Because remember, it's already traveling at 5 meters per second in this direction. So in other words, does it net travel in this direction? We don't know yet. We need to go through that calculation. So let us then write down the momentum conservation equation. So momentum conservation. So what is the initial? So initially what we have is we've got a system that looks like this. We've got our cart like that, and the projectile is inside the cart. And the whole thing is going at a velocity v2, which is equal to 5 meters per second. Then what happens is that the cart shoots out the projectile in this direction here. So the projectile actually goes in that direction, and the cart then moves at a faster velocity. So the cart then moves at a velocity it started off with V2, so now it goes V2 plus, let me call that Vc, so that is the velocity of the kart, and then the velocity of the projectile is going to be V2 plus, and then let me call it Vp for projectile, or ball, whatever it is that you want to call that, but I'm calling it positive because I'm not sure yet if the projectile net travels in the negative x direction. Once again, let's put in our coordinate system so that we know where we stand. So I'm going to call this direction positive here, so that's the positive x direction, and that's the positive y direction. So positive x is along the left, which is counter to our usual convention. Okay, now in this situation, let's write down momentum conservation. Momentum conservation tells us that the initial velocity of the combined mass was the mass of the kart plus the mass of the projectile, and the whole thing was going at 5 meters per second. So V2 must be equal to the final velocities of these objects once they have separated. The mass of the kart times its velocity, which is now V2 plus Vc, and then plus the mass of the projectile times its velocity, its initial velocity before it exploded apart or away from the kart, which was V2, and then plus the velocity of the projectile. So that's our momentum conservation equation. If we write this out, we find something quite interesting, namely that mc plus mp, we write it like this, times v2 is equal to, and here it's mcv2, so it's mcv2 plus mcvc, okay, so that's the kart velocity, plus mpv2 plus mpvp. So I've just basically multiplied this out. But what you can immediately see is mcv2 you've got here, mpv2 you've got here. So this and these two terms immediately cancel, and the equation that I am left with is this one. 0 is just equal to mcvc plus mpvp. Essentially, well, technically what we have done is this is now the center of mass frame. Okay, so what it means is it doesn't matter what the initial velocity of the kart was. What really matters is once the kart shot the projectile away from it, there was an impulse happening on both the projectile as well as the kart, and their velocities happen. It doesn't matter what the initial velocity of the kart was and the projectile. So in other words, it doesn't matter what V2 was, because you can see V2 drops out of the equation, so it's actually immaterial. This here is the center of mass frame, so in other words, it would be the frame as if an observer like us is moving with this thing at 5 meters per second. So to an observer moving at 5 meters per second in that direction, this thing actually stands still. So that the initial momentum is 0, and then the final momentum is just given by this expression. The next and final thing that we need is what is given to us is the fact that the velocity of the projectile relative to the kart is 0.6 meters. So that means that if I subtract the two velocities, I should get 0.6. I'm going to take the VC as positive in that direction. So I'm going to say that VC minus VP, so that's the velocity of the kart minus the velocity of the projectile, is equal to 0.6. So now what I have is I've got two equations with two unknowns, VC and VP. Now the rest is quite easy. I just solve for VC and I put it into the equation. I'm going to do that just for the one so that you can see what it looks like. So 0 would just be equal to MC times and then VC is 0.6 plus VP, so that's 0.6 plus VP plus MP VP, so that we have one equation with one unknown. Then putting in the values, the mass of the cart without the projectile is 2.5. Then it's times 0.6 plus, and then 2.5 times VP, and then the mass of the projectile is 0.5, and then times VP. Let me go over this way. Solving here, okay, and that's 0. Solving for this equation here will very, very easily just yield us the fact that VP is equal to minus 0.5 meters per second, and then resubstituting it into this equation gives us that the cart velocity is going to be equal to 0.1 meters per second. So as you can see that relative to the center of motion, so moving with someone, the projectile obviously is ejected in the negative direction. Remember, this direction is positive. The projectile goes that way. So it goes at minus 0.5 meters in that direction. And the cart shoots forward at 0.1. It shoots forward less because it's heavier. And then we can relate this whole thing to the total velocity relative to someone standing on the slope here. That would be 5 minus 0.1, which is 4.9, or 5 minus 0.5, which is 4.5 meters in this direction, and the cart now goes at 5 plus 0.1, which is 5.1 meters per second in that direction. And that finishes off this problem. Thank you.